Vou apresentar de que forma?
Hello, guys. Everyone. Good luck to everyone. Hello, guys. Good
Hello.
luck to everyone for presenting and also Victor.
Thank you.
I am with you.
Thank you.
Eu preciso abrir minha câmera.
Ih, meu Deus.
Som, é.
Hey guys, how's it going? So please turn on your camera since we're gonna show your pretty faces to the world. Hello, hello. We're still missing a bunch, but that's life, right? So 3 minutes. Hello, hello. Hello, hello. All webcams on. Sid, could you please turn on your camera? Okay, is everybody ready? So we start. Good afternoon, everyone. Welcome to my dear students of batch 1542. Welcome to the public and the people watching us live on YouTube. I'm Chloe. I'm the bootcamp manager, and I had the pleasure to work and follow the progression of this batch. Allow me to share with you a little presentation that I did with love, so that I can tell you more about the program of today, what we're going to see today. So be very welcome to this demo day of the batch 1542. Let me reduce this. Today is a day of celebration, right? Since we are showing to you and presenting to you the product of 9 intensive weeks of work. And I am sure that everybody, or at least some, are already feeling an inch, because it's the end of not so course, but also a social experience. For non-Portuguese speakers, it says, me waking up on a day without le wagon. And we can maybe ask our alumni how they feel and how is it. Here is batch 1542, so that you can see their pretty faces. A bit more about what we do here at Le Wagon. I highly suggest that you enter our website so that you can know more about the course in itself, and also what are the outcomes for those people who now are gonna enter the job market of data science and AI. We'll talk more about next session after they present their project, which is the main reason why we are gathered here today. Here is my beautiful colleague, the staff of Le Wagon. You might recognize me on the bottom. Here are our teachers, and I would like an ovation, not standing, but ovation for our teachers. Without them, none of what you're going to see would be possible. And also, of course, our TAs. So I've talked enough. Now I'm going to let you present your projects. Are you ready? Show me the codes. I'm going to call first No Latex, Diago, and Philip. Floor is yours.
Yeah. Hello guys, let me just share my screen for the presentation. Good afternoon all. So we are the No Latex, and I'll be presenting for you guys a little bit what we did. So let's start. We are the No Latex team. As you can see by the photos, the team are composed by me, Arthur, Diego, and Philip. The idea from the project came from Diego, who teaches physics and wasn't satisfied with the websites and programs that convert handwritten math formulas to LaTeX. So we decided to help him out and create our own website, which analyzes handwritten math formulas in order to generate LaTeX code throughout AI. And what does that mean? So let's take a look on this math expression photo. It's pretty bad, right? So our goal was to transform this bad image into something better and easier to read, because it's much more pleasing to read a math equation digitally than like this one. And after a lot of pre-processing steps that we will explain later, you can see the final result, and it works very, very well. And now you may ask, why Diego wasn't satisfied with the other methods. So we have three options available to do this conversion. Option 1, write it on Math editor on Microsoft Word, which is very slow and limited. Option 2, know and use LaTeX, but to do so, it would require a lot of proficiency in LaTeX and would demand a lot of time to do so. Or you could use the better and easiest option, no LaTeX. And now we are going to show how simple it is to transform the image on our website, no LaTeX. Please, Diego. Now you can go ahead and show everyone how it's done and how easy it is to convert image to LaTeX.
Hello again, guys. Let me just show you how easy it is. Just grab an image from your computer, upload in the website, and after that, it's just clicking a button. System is running, and here you have the LaTeX code and the generated image from this LaTeX code. It's as easy as that. Now I'll go back to the slides, and Philip is gonna tell you a little bit about what we did, how we achieved it.
Thanks, Diego. Okay, are good? Yeah, okay, perfect. Yeah, so let's look a bit behind the scenes of this very beautiful product. You can actually see the workflow that's happening behind, or that we've been also using for training the model. So you have an image as just shown by Offer. We do some pre-processing under the hood, which I will explain a little bit more in detail in the next slide. Then we use a computer vision model to recognize the symbols and also categorize them, or recognize them. Then we use a language model to use to actually transform these symbols and digits that we've recognized into actual LaTeX code, which will then be the output. And the translation of the LaTeX code is then actually done by the web browser so that we can display it properly. To start at the beginning, let's have a look at our data set, which we have there. Yeah, just to give you a quick overview of what data set we used to accomplish our goal. So we had a data set of 10K images, all of them handwritten limit equations, and they were separated in 10 times 10K batches. And each of these batches included the images as well as the target JSON file. And altogether it was 11 gigabytes. In the target JSON file, you could find not only the LaTeX expression, but also the bounding boxes, which is very important for the computer vision model that we used. And Diego will explain a little bit more in detail why this is important later. For now, just a brief overview of the data also in some graphs, just some examples of the initial exploration that we did. So we, for instance, looked at the length of the later LaTeX expressions. Is there a good variance within that, so that we're able to not only transform short expressions, but also long ones, as well as we looked at in the bottom right, you can see the distribution of tokens that we had within the data set that we trained the model with. This is around 60 tokens that we're now able to recognize. In the total data set, it was around 90, but that would have required more iterations of training the model. And on the top right, you can also see that we had a look at how big the images are. And as you can see on the scaling of the X and Y axis, the images tended to be a rectangle, which is an important fact that brings me to the image pre-processing. So image pre-processing we did, first of all, we had to sort out all the low quality images. As you can see here on the very first picture, even hard to read for a human, what kind of formula it could be. So we had to find out a way to sort out, in this case, low contrast images. After that has been done, we converted the images first to grayscale, and later we binarized them, which is a step where we basically define the threshold in which the algorithm decided whether it should be, the pixel should be white or black. And with that, the symbols are even more clear in the picture. And last but not least, that brings me back to the image sizes. We had to resize the images, as quadratic images work way better for image recognition models as rectangle images, because the models might assume that the width and height of an image actually might be a contributing factor of what to recognize within the image. This was actually a rather complex step also, because we had to take care of resizing the bounding boxes as well. And yeah, with that, we thought we could just simply take the data and train our own models, but we ran into some challenges, which Diego will explain a little bit more in detail.
Hello again, guys. So what we are trying to achieve was to find out the position of each element into the photo. And to do that, we are using a YOLO model. Why did we choose this model? Because the model does two things at the same time. It gives us the bounding box, a prediction of where the things are, and it also classifies the things. So we get both things we need. We get the position of things and what the thing is. And with that, we can reconstruct the tokens into LaTeX code. But as Philip said, we ran into some problems, and I will explain them in a bit. So our challenges was mainly computer power. We didn't have access to a good GPU or a really good computer to train. We also had memory issues, because every time we tried running our own model and training, our memory was getting overloaded because we don't really have too much memory. And because of all that, we are facing like high training times. We had to wait a really long time to get a result. So one way to solve this would be try running things in the cloud, but even then we have other problems, like mostly cost-related problems, because every test we do is paid, and to train the model completely, it would cost too much for this project. So how did we solve this? We use a pre-trained model. So we have many advantages, mostly on the side we are having challenges like computing power. And the drawbacks is that we kind of get limited into the customization of the final product. And we are currently limited in the kind of math we can handle. So a little bit about the model we are using. The model was trained with the same data set we were working before. It has more than 110 layers and more than 28 million parameters. And the limitations of the model is it's only able to predict 60 characters, and it's highly specialized in limits. So lastly, the next steps we could do to keep developing this product is to set a better data structure, so we can load better, like we can use better than the resources we have at hand. Like if we set up a generator, we could parallelize the tasks and make operations on the dataset load more data while the model is training, so we can save some time and some resources doing this. And further steps would be developing a custom language model and to train the model with a broader data set, so the model is able to handle other kinds of math also. So thanks for your attention, guys. That should be all. So
Thank you. Congratulations, guys. Awesome work. Thank you very much for being the first ones to present. We continue our presentation with the next group. I'm calling Victor for COVID-19, and I take the advantage to say congrats and thank you to Arthur too, that I forgot in the beginning. So let's go for the second project, COVID-19 detection with Victor.
Thank you, Chloe. Okay. Hello, everyone. I'm here today to introduce our final project, an innovative app to classify X-ray images between different diseases. Our goal is to create a user-friendly tool that can help detect the presence of COVID and other two diseases, pneumonia and opacity. The principal dataset used was COVID radiography database from Kaggle, but we collect data from multiple data sets for increase the balance data between the classes. So we put these links here. We train a convolutional neural network to learn the patterns of figures based on the previous classification of the image, and we find 82% accuracy in the test analysis. This is the model, and you can see 1, 2, 3 layers, convolutional layers, and 2 dense layers. And this is the result by loss function and accuracy in training and validation tests. So, for predict, as you can see, the interface is simple and easy to use. Users can input an image, and the app provides real-time analysis and classification. For example, I put in a normal, or in other words, a health person, and the image push in API and results in probabilities in 4 classes, and the best probability is the class, the winner class, your target. So you can see in this graphic and in this table. The model is very efficient in classifying images of COVID and pneumonia. For example, you can put this image, things, and edit. And other example, pneumonia example. And these results. However, it's limited in difference opacity from the health people images. So, in opacity, is wrong, but in your other example, you can see correct results. But opacity is not a single disease. It's a diagnosis that can represent several diseases. This is probably why the model has difficulty for classifying. So, to conclude our presentation, we want to reinforce the importance of developing applications that help diagnose disease and the need for a constant improvement of these tools. Thank you very much.
Thank you. Congratulations. Awesome work. Thank you, team. I'm calling now the third group, which is classifying the brain on music with Jonathan and Lorena.
Thank you, Chloe. I'm gonna share my screen with you all. Not sharing. Mm,
Maybe I can try to share my screen if necessary.
right. Yeah, now it's working. Okay, hello everyone. Thank you for being here watching us. I'm Lorena, and I'm gonna present the project I did with my teammate, Jonathan. Our project is about classifying the brain on music. I will contextualize a bit so you all can understand where this idea came from and why it is important nowadays. The idea of the project came from studies where images of the brain were recorded and brain features were extracted to perform the music theory prediction. The machine learning models are called decoding models. They find applications in neuroscience, psychology, and diagnostic medicine. Particularly decoding acoustic information like this holds promise for the development of technologies that connects our human brain with external devices. So when we learn and understand better the brain, we can develop and potentially enhance this kind of technology. The image here that we added was extracted from one of those studies. It was a very complex study that we're not going to enter in this matter in the presentation, but if you have curiosity, you can access the links of the papers on our additional infos. It is very interesting because they recorded the images and then they treated the images using pre-processing techniques and came up with some predictions as well. So about the objective of our project. For our project, the data was already ready for immediate utilization. So the data came from a study like the one mentioned before. So it was already pre-processed, which means they had already transformed the images into numbers so we could use in our models. The main objective is to take this data and classify these brain images that were taken while listening to music into 5 different genres: ambient music, country music, heavy metal, rock and roll, and classical symphonic. This is a basic project flow chart that I created so you can understand better how our work flows. So first we have the input data that I mentioned before, then we did a small pre-processing, and then we used it in our model training, which was a logistic regression model. And then we're gonna have the output, that is the predicted labels. I'm gonna show you now a little bit of our data set. So our data consists of trained, test, and label data sets. To keep you up with the languages we use in data science, I wrote it here so you could understand better what this is about. So the trained data is like practicing with examples to learn how things work. And the test data is like taking a quiz to see how well you remember what you've learned. And the label data is like having answers to the quiz, telling you what each example is. So basically, in simple words, our data set are the images already translated to numbers, the language that computers understand. So you can see here the data set that we used. This is our numbers that we allocated in a table. This is the images that was translated to numbers and we allocated in a table that we're going to use later. This data that you guys are seeing here was recorded from only one person. There are 22,036 features in each brain image corresponding to blood oxygenation levels of the auditory cortex, that is an area of the brain. So due to these 22,036 features, this is a problem with high dimensionality that we call in data science. making the task a relatively challenging multi-way classification problem. So let's skip to the fun part. That is the predictions. I'm gonna upload a CSV file here that we're gonna use in our model. Just thinking a little bit. Oh, crash, please. So you're gonna see a table like the one I have shown you before, but with only one sample, so we could make a faster demonstration for our predictions. Here we go. And when we hit the button predict, the model takes these values from here and run the code to give us the predicted label. So let's wait just a little bit. And here we go. So country music it is. We can see here 72.5% of certainty of this result, which is a very good result for a multi-class classification problem. And that's it. This is the model running. And if you're curious about the studies that I said before, we have an additional information section. And here you have about the data set, the contextualization, and the papers I cited. And the teammate, that is me. And Jonathan, you can access our LinkedIn and GitHub with our projects. That's it. Thank you so much for listening and for your attention, guys.
Congratulations. Awesome work. Guys, it's already our last group. I'm calling Isaac with Life Sentiment Tracker. Isaac, the floor is yours. I'm showing the chat too.
Okay, so our project is Life Sentiment Tracker. As the name might suggest, our main goal here is to track the sentiment of a text while it's being typed, so it's all done live. To accomplish this, we've used the Veda sentiment model. It's a pre-trained model. It will classify text into 3 distinct categories: positive, neutral, and negative. And by doing that, it has 88% accuracy, just about. In order to accomplish this, it weighs the importance of each word and classifies it on one of the 3 categories. So, for example, saying you love something will be extremely positive, whereas saying you like something will be quite positive, but not as positive as saying you love something. Since it's a quite modern model and it was trained in a quite recent data set, including Twitter posts and online movie reviews, it is already able to understand very common abbreviations and some emojis as well. But while we were testing at the beginning, we noticed that these categorizations were not as accurate. So, for example, using the abbreviation LOL would not have the same result as typing out laughing out loud. Laughing out loud was much more positive than just LOL. To fight this, we've implemented another process to our pre-processing, which we've nicknamed our slang translator. So we grabbed 2 different data sets from Kaggle and then manually judged what we thought would be relevant or not. Thank you, Bruno, for going through that. It was quite an extensive work. So now with our end product, when the user types an abbreviation, what the model is receiving is actually the full extended phrase. Now for a quick demonstration. For example, if I type, I love apples, it's quite a positive phrase, which you can see by the size of the emoji. Here on our pie chart, you can also see it's 67, almost 68% positive. But if we change to like, for example, that goes down quite a bit. Or for example, now we can check that LOL will be just as positive as laughing out loud. For a more complex example, you can say something like, I love my job at the emergency room. I found that emergency is quite a negative word for the model. In the end, it becomes quite neutral. And here we can see how each word affects the sentiment. So each unit is one of the words, so we can track it. So love goes quite high, and as soon as we reach emergency, it goes back down. If any of my colleagues have another phrase they would like to try out, we're open to suggestions.
It's like, what about I have back pains from coding all day?
I have back pains from coding all day. Let's see. Quite neutral. This will happen mainly because since the model is weighed per word, it does not check the overall context of the words, and most of the words in the phrase were indeed neutral. So as soon as it reached pain, it's quite negative, and it remains negative from there on because everything else is neutral, so it doesn't change again. We also have our crew tab. Again, I would like to thank Bruno. Without him, nothing would have been possible. This was a lot of teamwork, a lot of sharing responsibility. We've prepared a few quick fun facts about each one. If anybody wants to, if anybody wants to check our LinkedIn, if anybody's hiring, and that's it. Thank you all for your attention.
Awesome! Congratulations. That's awesome. Team, I'm very happy to announce that you're now officially graduating data scientists. Congratulations to all. I hope you are as excited as I am and proud of yourself because it was a lot of work and someone has their mic still on, but that's okay. Very, very honored and proud. And I can see that few of our teachers are present on the Zoom, and I'm sure that they share my feeling. Congratulations. You deserve all the good compliments that comes your way because you undertook very complex challenges. So once again, very proud of what we showed today. And I guess this is concluding 9 weeks of intense work. Congrats, bravo, as we say. And I would like to conclude this saying that if for you who watch us online on YouTube right now, or maybe later, if you're convinced that you want this for yourself too, and you would like to be able to build such incredible platforms in the future for yourself, I have a great news. We have more batch opening in the future, and I'm gonna be more specific. Next batch starting, whoops, not now, thank you. Next batch is starting in April, so be sure to take all of your informations if you want to make part of the Wagon adventure in April or in July, or more further in 2025 to change your life through tech. Thank you for your attention. Thank you for your presence, for your disposition, and be sure to follow us online on all of our socials. And a great afternoon to all. And again, congrats to my students. I'm gonna close the YouTube so that we can be just between us and stream. And that's about it.